Okay, so here's the question. I would like to get from here to where Kiara is. So in order for me to do that, I'm going to walk a path. And let's see, I'm going to go a path this way. And then I'm going to go over here. And let's just say I go this way. And now I'm to where it goes. Okay, great. I'd like to measure the length of that path. Now think about that logically for a moment. Was my path straight? No. If it was straight, life would be easy. So I have a situation where I'm here and I want to get to here. Now, if I had the ability to fly, or at least float, I could raise myself up. Could I have made that path straight?
Yes.
So, would you agree that's the shortest path from point A to point B?
Yes.
That seems reasonable. Is that the answer? The length of that path? No, that's going to be a little bit too small, right? My answer should be a little bigger than that. Should it be a lot bigger? Maybe, but it's definitely going to be bigger. So that's not going to be a very good estimator. If I just said, let's find the length from here to here, that is an estimation, but we all agree it's too small. So what if I did something like this? I think I have a few different line segments. If I found that length, would that be a better estimate? Would it be the answer?
No.
Would it be closer to the answer?
Yes.
Mhm.
So how could I improve upon this still?
Smaller lines.
Okay? And more of them?
Yes.
What do you guys think? More line segments?
Yes.
So let's suppose I have a whole bunch of really short ones. If I had a whole bunch of very short line segments, would the sum of those lengths be even better?
Yeah.
Yes.
You smell it? What does it smell like?
Limit.
It smells like a limit. Oh yes, there's a limit in there somewhere. The limit will be obviously as the lengths get shorter and, like Cece said, more of them. So how do we set up this? This is to find the arc length, the length of the curve. So what I'm going to do is I'm going to take one of these little pieces here, I'm going to blow it up huge. There's the arc. There's the line segment. Make a right triangle here. Okay? This is the change in x. This is clearly the change in y. What symbol do we use for arc length? Does anybody know? It's odd choice, but what symbol or letter of the alphabet? It's universal. It's the same all through math and science. S. S for arc length. Well, what do we use for slope? M. Yeah, it makes just as much sense. Right? We use an M for slope, we use an S for arc length. So universally, S. So this is the actual change in the arc. I don't know what delta S is. That's what I'm trying to find. But can I use the length of the line segment as my best estimation of the length of the curve? Can I do that?
Yeah.
The shorter the line segment, the better the estimator will be, right? Because there's going to be a limit coming on. Now, we did this at the beginning when we first did the applications with the derivatives. Do you remember I said the tangent line is escaping the curve, and we used the value on the tangent line to estimate the value on the curve? We said the actual change on the curve, we use deltas. The change on the tangent line, we use d. So what we do is we say we're going to call this ds. It's also called the incremental or differential change. But notice on the line segment and on the arc, I'm using the same x for both, aren't I? Delta x is the same for both. And so a lot of books will say, well, I'm going to use a dx, I'm going to use a dy. It really doesn't matter. Some books will use a delta, some will use a d. The incremental change, the change on the line segment is exactly the same for x as it is on the arc. But that is not the same. So what we're going to do is, not x, s. We are going to estimate this with this. Now, can you tell me exactly what this is? Yeah, I think we have a way of doing that. It's a right triangle? Pythagorean theorem, beautiful. I'm not even going to bother using these guys. I'm just going to use these. Is it correct to say that this is equal to the square of delta x plus the square of delta y all into the square root?
Yeah.
Is that correct?
Yes.
Now, there's going to be a limit. What am I probably going to send to 0? What do we usually send to 0?
Delta x.
Probably the delta x. That makes sense. But not yet. We'll get to that. Now, I don't like the way this looks because I don't really know how to manipulate this yet. So let me ask you a question. Can you factor out an a squared from this? We've done this kind of algebra many times in this class. How would you factor out an a squared?
A squared on the left side, open brackets, 1 plus b squared over a squared.
Beautiful. So you know what I want to do? I want to factor out a delta x squared from this formula. So based on what you just said, I want to do this as delta x squared times 1 plus delta y squared over delta x squared. Would that work for everybody?
Yeah.
You don't like that?
No, because it's square on the inside.
Well, no, I'm just talking about that part.
Okay.
Just the inside. Would that work?
Yeah.
We're going to take the square root, yes. I just want to get that part first. So if I now put all of this under the root, then this becomes 1 plus, how about if I rewrite that as delta y over delta x quantity squared under the root, and can I put this guy on the outside?
Yeah. That's just
Delta x can't be negative. Can delta y be negative? Yeah, delta y could go down, but delta x is always going to be positive, and that's important because then I don't have to worry about absolute values and crazy things. So algebraically, the best estimation for the change in the arc length will be this quantity here, which is now starting to look very calculaic, isn't it?
Alright. Could we, I feel like I'm rushing ahead, but can we say the change in y or the change in x is also equal to the slope?
It is the slope of something. Yes, it is the slope of this line segment. That's exactly what it is. But from a calculaic standpoint, there's something way bigger than that. We're going to try to show it's the instantaneous rate of change, which goes from just slope to what? The D word.
Derivative.
Derivative. Ooh. So we're not there yet, but you're going to see this link. So now, the actual change, the actual arc length, can be estimated by the sum from I equal 1 to n of these guys, if you will. I'll write it this way. So I have there's the first delta s, there's delta s1, delta s2, delta s3, delta s4, and so on. I have n of them, I'm adding them all up. I'm sorry. This is equal to this, sorry. It's estimated by the ds's. So that's what it exactly is. Here's my estimation. The thing I'm going to end up taking a limit of, let's put that in there. 1 plus delta yi over delta xi, because it's the ith one, squared under the root delta xi. So that's the first line segment plus the second line segment plus the third line segment, on and on and on and on. I just added the lengths of all n line segments. We would say that is a reasonable estimation. It is not equal because there's always going to be a little bit of a gap here. But if I take the limit as these guys, these delta x's go to 0, we know we're going to get an equals. That's the Riemann sum part. This one I cannot skip. I got to do this whole thing. So now I can say S equals the limit as the norm of the partition approaches 0 of this. This is the cool part. This is my favorite part of this. This strange problem we're doing right now, we actually will do in Calc 2. We will actually do in Calc 3. But each from a slightly different point of view. Okay? Isn't the limit of a sum the sum of the limits?
You dropped the squared.
Did I drop? Oh, thank you, Chase. Isn't the limit of a sum the sum of the limits?
Yes.
So in theory, can I take this whole limit and move it right into there? Yeah. So now I have the sum of the limits of a bunch of square roots. Now, isn't the limit of a square root the square root of the limit?
Yes.
Remember, that's the composition of functions. by the way, just in case you forgot. So if I said the limit as x approaches a of the square root of f of x, that's equal to the limit as x approaches a of f of x, all under the square root. That's probably the single most important limit property, is the limit, right, of a composition is the composition of the limits. That means I can take this limit and move it inside the square root. Ooh, so now I have the sum of the square roots of the limit of 1 plus something. Right, but the limit of 1 is just 1. So really, I only need the limit where? Here. So now I have the limit of something squared. Wait a minute. Isn't the limit of something squared just the square of the limit? I've now worked the limit. Oh my gosh, this is crazy. I just worked the limit all the way onto the inside. So I'm going to rewrite this now. Oh, I'm sorry. So I'm going to rewrite this. I'm going to write it with the limit in the appropriate place. Now, the norm of the partition is the largest such delta x, correct? But if I move it inside here, it's only looking at that one. It's not looking at any other one. On the outside, it was looking at all of them. But if I move it in here, there's only one in here at the time. So I can just say the limit as delta x goes to 0 of delta y over delta x squared. I said you can move it all the way to the inside. Now, this to me is the most beautiful part of the calculus. And unfortunately, I have never been able to find what we just did in any textbook. I have 30 calculus books in my office. Not one of them has any of this. They have the result, but not the why. Hopefully everybody sees this is kind of the ODA, right? Pythagorean theorem. We did a little bit of clever algebra. Now we're doing the Riemann sum. But by me manipulating the limit and moving it all the way to the inside, basically just using a simple limit property, I can now say this is equal to an integral. And again, for lack of a better name, just for now, let's just call that A, and we'll call that B, just to give it limits of integration. But the question is, what's my integrand? This is the coolest part of all. And you already know the answer because we've already said it. Going back to literally, I don't know, second or third day of class. If I'm using function notation, we write it this way. If I'm using x and y, this is the exact same thing, right? The change in y, this is the change in y. What do we call this thing? Do we call this the definition of the derivative? Isn't this technically f prime of x or dy dx? Again, depending, am I using function notation or am I using...
You forgot the delta x on the no one.
Oh, thank you, Chase. Thank you, Chase. There should be a delta x on the outside. Yes, good catch. Question is, I want to write this now as a definite integral. This is what we call f prime of x. This is dy dt. They're the same thing depending on which notation I'm using. What does that make this?
Yeah.
That's dy dx, isn't it? I'm not using function notation. I'm just using y equals f of x. Oops. To me, this is the most beautiful part of the calculus that we're learning, is that I can now write the answer. And this, folks, is the formula for arc length of a curve. And we could not have gotten it without doing this. Now, the formula is fairly simple to execute. It's fairly simple to execute, but after that, it can be kind of difficult to do. And I'll show you what I mean. Let's do a couple of fairly simple things. All right. I want to find the length of the curve y equals, how about sine x from x equals 0 to x equals pi. We'll keep it simple. So one hump of a sine wave. Okay, so I want to find that. Okay, that doesn't seem too terrible, right? I want to find one hump of a sine wave. So y obviously is sine x, and x is between 0 and pi. Well, I know those are going to be my limits of integration. So what is my integrand going to look like? So there's an order of things you want to do. I always say start by doing the derivative and then do 1 plus and, kind of do it in order. So the first thing I'm going to do is, what is dy dx?
Cos x.
Cos x. So what's 1 plus the square of dy dx? Because that's what's going to go inside the integral ultimately.
Sine squared x. Or 1 plus cosine squared.
Okay. Is there any trig identity there?
Yeah.
Now, 1 minus there would be a trig, but not 1 plus. Okay. So now I can say with absolute certainty, the length of the curve, which we'll use s, is the integral from 0 to pi of the square root of 1 plus cos squared x dx. You with me? Was that hard to state? No. And now what? You're going to like this part best. Now we wave at it as we walk away and go on to the next problem. Why? Because that can't be integrated. And in fact, 99.999, a few more nines, percentage of all problems can't actually be integrated. That is the formula for Arclength. But actually integrating it is a problem because we have something under a square root. The only way I could do this is with a u sub, but I don't have a chain rule factor sitting on the outside, so there's anything I can do. I can just, so we're going to look at some of these kind of.
So then why do we have this as?
Because the ones we can do, and then we learn tricks later on in the later semesters. In Calc 2, we learned some tricks that open up a whole bunch more things because we're introducing new forms of the math. Now, it turns out we can do a few of these. I have fun with this one. There are exactly 3 functions that exist, and then, of course, variations, scalar multiples of those functions. There are 3 functions that exist where we can do this. That's it. 3.
Even with all of the techniques in Calc 2 and 3?
Well, with Calc 2, we learn more techniques, but then we also learn ways of doing estimations that are really accurate. And that's what ends up happening in life. It sounds weird, but very few things in real life you actually get equals. A lot of times you are get what's called asymptotic convergence. This is one of the main points of next semester. It's called Taylor series. We do things, I can write, and I can show you this on Desmos later, I can show you a simple polynomial that looks just like a sine wave for a while. And if I want to do things with the sine wave, if I do them to the polynomial, I'll essentially get the same answer. You go, that's unbelievable. It's so cool. This is what we actually do in reality. Things that we can't do directly, we find indirect ways that are so close that it may not make a difference numerically. I can show you, by doing a few terms that you want decimal accuracy, I can guarantee absurd number of decimal places with just doing a few steps of polynomials rather than nasty stuff. That's Calc 2 stuff. So when I tell you Calc 2 is primarily for the integrations we couldn't do directly. We learn other tricks. We can't do it all this semester, it's just too much, but Calc 2 is literally, this is Fellowship of the Ring, Calc 2 is the 2 towers. Meaning the first day of Calc 2 will feel like the next day of this class. Literally, it's what is the very next thing we would have done if our semester had kept going. And then you start learning more techniques. Calc 3 is Calc 1 again in 3D, quite literally. Calc 2, the follow-up is Math 255 differential equations. That's the follow-up to that class where you use all the Calc 2 techniques. You actually don't use Calc 2 techniques in Calc 3 at all. If you ask the Calc 3 students, how many times have you used a Calc 2 technique in this class? They'd think for a moment and say, we haven't at all. This is the main thing you need for Calc 3 because you're learning all of your calculus in 2 dimensions, and there you just apply it to 3. Not the techniques for the special stuff. That's what Calc 2 is, more the special stuff. But Calc 2 doesn't have anything abstract. Calc 1, we do a lot with limits and abstract stuff that, tricky. So this is the nature of a lot of the problems, but not all the problems. So let's do a problem that we can actually finish. So let's consider the graph y equals x to the 2/3, and let's say we want to go from 1, 1 to, how about 27, 9. And by the way, most of the time, an arc length problem, they'll give you from point to point, not just the x coordinates. So if I were to draw a picture of this, you guys remember what this looks like? What's that guy called again? That point. Cusp, good. I'm giving you a picture that has a cusp in it. And I'm asking you to find the length of the curve, basically from, let's say, from here to here. So that's the point 1, 1. That's the point 27, 9. Oops. Now, if I simply drew the line segment connecting the 2 points, that would be a very crude estimation. It would be too small. But the reason I want you to consider that is when I'm all done with this problem, I'm going to get something really ugly. I'm going to get a really ugly irrational answer. How do I know if I'm right? Well, we'll just hope really hard, right?
You can do that. It's just
I can
fine.
compare it to that. This is what you always want to do. I'm going to calculate this because I can in this case. But I have no idea if I did the problem right. But is this calculation hard or easy? If you did this one in 9th grade, right? Distance between 2 points. What is it? It's going to be 26 squared plus 8 squared under the square root. That's your answer. I'm going to compare it to this. And this answer ought to be a little bit bigger. And if it is, can I have faith in my answer? If it's smaller, that would be bad. If it's 10 times bigger, that's probably bad. It should be a little bit bigger. But that's how you check it. I'm not worried about the check. I want to get the answer. So let's go back to the beginning. I said what we do first is we find the derivative, and then we work from there. This one is kind of cool because it's not that complicated. So what is dy dx? That was pretty complicated.
2/3 negative things.
All right. What is 1 plus the square of dy dx? I'll do my part. What's the square of that? Squared.
4 9
X to the 1/9.
minus 2/3.
How about negative 2/3? Double the exponent. More coffee. Okay, this is correct. I don't like the way this looks. In fact, that's a negative exponent. So how about if I first go like this? Is that correct? Now, this is all going to go under a square root at some point. So rather than have 1 plus a quotient, can I make this all one quotient? That might be more useful. In other words, I only have one denominator. Can I make this into one quotient? Yeah, want to be 9x to the 2/3 plus 4 over 9x to the 2/3? Now, finally, I want this, which would clearly be this kind of creepy looking quotient. Okay. Now, my denominator is a perfect square, isn't it?
Yes.
I mean, didn't it come from squaring, x to the 2/3 in some capacity? Can I pull that out and write this differently?
X to the 3rd.
To the 1/3. Okay. Whew. That's a lot of work. Does everyone agree that's the square root of the 1 plus derivative squared? Okay. Wow, okay, now we can write our integral. So now we can say with certainty, the length of the curve is, well, the x values are ranging from 1 to 27. My integrand is the square root of 9x to the 2/3 plus 4 all over 3x to the 1/3 dx. Well, that looks worse than the last one, doesn't it? You know, but if I were to do a u sub, what would have to be my u in this problem?
9x to 4.
Yeah, it would have to be the part under the root. That's the only part I can't mess around with. So just for fun, because that is our primary goal on a daily basis, if I were to do this as a u sub, what would my du be?
The 6x to the negative 1/3.
Well, yeah, like I got a x to the negative 1/3 sitting around. Wait a minute. Do I have an x to the negative third sitting around?
It's right behind me, isn't it?
It's right there. Oh my gosh. I have the chain factor, don't I?
Yes.
So let's rewrite this bad boy. All right. Let's write this as 9x to the 2/3 plus 4 to the 1/2. Wouldn't this be then 1/3 x to the negative 1/3? Because the 3 is on the bottom. Now, what do I need it to be? I need a 6. Well, that's actually the easiest part of the problem. All right. So how about if I do this? Get it out of the way. Now, what do I want in that position?
6.
So what do I now do? That? Now stare at this really quickly. 1/6 times 1/3 times 6. Isn't that 1/3? And now I'm back to the original. But what do I have now? That's exactly the du that I needed. Ooh. So we can do this one. Now, I changed the variable. Now I need to change the limits. So x was ranging from 1 to 27. You might need a calculator, but at least it's going to be rational. When x is 1, 1 to the 2/3 is still 1. 9 times 1 plus 4 is 13. 27 to the 2/3. That means cube root squared. What's 27 to the 2/3? Cube root squared would be 9. 9 times 9 plus 4, that would be,
85.
I think, 85.
Yeah.
Those are strange limits, but at least they're rational numbers. I like that part. All right, so let me erase this, just that much. So this became 1/18, the integral from 13 to 85, yikes, of what? U to the 1/2 du. Oh, well, that's not bad. That's not bad at all. Hey, that's pretty simple, isn't it? I mean, getting here was kind of gnarly, but. So what is the antiderivative of u to the 1/2? U to the positive 1/2, so the u to the
2/3
Careful.
times.
U to the 3/2 times 2/3, but I already had a 1/18. So if you can't do it in your head, do it off to the side. What's 1/18 times 2/3? 1 over 27. Are either 85 or 13 perfect squares, or do either one of them even have factors that are perfect squares? No, so there's no simplifying. The reason I point that out is I'm going to have a 13 to the 3/2. I can't really do much with it. In general, if I have 13 to the 3/2, is this correct? Is this correct? 13 times root 13. Is that the same thing? Yes. Which one's better, left or right? This is an absolute. This isn't an opinion. I'll give you a hint. How many times did you write 13 on the left? How many times did you write it on the right?
Twice.
So which one's better?
Left.
Left. The left is simplified, the right is not. Yeah, so in other words, Unless I had a factor of a 4 or a 9 or something like that, I can't do anything with it, so we simply leave it alone. So my final answer would be what? 1/27th, 85 to the 3 halves minus 13 to the 3 halves. Pretty ugly looking. I said it was going to be ugly. I said it was not going to be rational. Can we do this on our calculator if we needed to?
Yes.
I'm creating a walkway outside of my house and I need to know how much material. So I'm going to go down to Home Depot later on today. And this is how many feet. That's not going to work well, is it? They're going to look at me like I'm crazy. You know, the guy says, yeah, I can do cube roots in my head, but not square roots in my head, or something like that. You know. So let's give a numerical value for this. That is the answer. Do I? No, I don't have actually have to calculate. That is the answer. But I'd like to know how big it is because I said I wanted to compare it later on.
27.288.
You got? Does anyone else get that? He said it's approximately 27.288. I see multiple nods. Okay, that's the answer. That's a decimal approximation, which is very useful in any science situation. I said I'm hoping I did this right. Do we have any certainty that we haven't messed this up entirely? Is it possible we could have messed up the coefficients? In fact, is that probably the most likely error we made errors is maybe someplace here? It's possible my answer could be way off. I did great calculus, but bad arithmetic. So here's what I'd like you to do. I would like you to compare it to the length of the line segment, which we said before is 27 minus 1, 9 minus 1,
27.202.
27.202
about.
What did we say our answer should be? Didn't we use words like it should be a
Bigger.
little bit bigger? What do you think? Is our answer a little bit bigger?
Yes.
Yeah. Now here's one of the things that always kind of mystifies people. I walked back to Kiara earlier and I went through your desks. If I had made it straight and found that length, the amount that I walked, believe it or not, was probably only a few inches further, not 10 feet further. A lot of people always confuse that. If I drew a triangle with a really long side and a really short side, and then I drew the hypotenuse, the long side and the hypotenuse are going to be almost the exact same length. There's not going to be a huge difference between the hypotenuse and the length. Meaning, in my original picture, my line segment and the curve are actually going to be absurdly close. Now, I have fun with this one because every day I park on the outer rim and I walk towards this building. And in the process of walking towards this building, there's cement that goes kind of sideways, and then there's a whole bunch of arc chips. Does anybody know what I'm talking about? You're walking towards the front of the building. Now, I laugh every day when I watch people walk on this. Now, what I do is I walk sideways, and then I walk forward so I don't have to walk through the bark chips. Every other human being that I see always walks through the bark chips because they're going to save so much distance. By the way, I've measured it. You save about 1.5 inches. But every person, when they get out of the bark chips, first thing they do, they stop, they bend down, and they check their shoes because their shoes now have bark chips. Anybody ever done that before? No matter how hard you try, when you walk through the bark chips, they're going to find their way in your shoes and under your soles of your feet. If you have flip-flops, it's way worse. And I laugh because every single day when I see people do this, they always stop and check because they have bark chips in their shoes because they wanted to save time and distance. When in actuality, they're not even saving 2 whole inches by cutting through. So a lot of times we kind of mistakenly get this. Now, I wanted a really quick and dirty estimation. I could have just found the length of the line segment and said, yeah, that's shorter than what it is, but the real answer isn't going to be a whole lot more unless I decide to loop back and forth multiple times. So the actual answer is this. We did a quick and dirty estimation. It was close. That gives us confidence that this is correct. That's all. If these were extremely different, I'd be very suspicious. Now, the reason we could do this problem was because the specific function I chose when we did the problem from beginning to end, it created a chain rule factor. We didn't do that. The nature of the problem, it was like that. There's only a few problems that we can do in Calc 1 where we will actually be able to complete this based on chain rule factors and stuff. So that's the one I want to concentrate on. A test question, a fair test question, and if you look in the homework in any calculus book, the instructions are usually the same. Set up the integral to find the arc length. What does that mean? Set up the integral to find the arc length. That means this is the answer, like the first problem I did. The answer is the integral, because the vast majority of the time you can't actually integrate that. Even when you learn higher techniques, you may not be able to integrate that. That's okay, because we have computers, we have ways of doing extremely accurate calculations, even if we can't find the antiderivative. There's always ways around it. But if I don't have the correct integral, no computer's going to help me on this. I have to tell the computer this is the question I want to answer. Now let's do one more of these before we move on to the second thing. Today I'm going to complete the entire lecture before we take a break so that afterwards it'll be all review. Because we're doing 2 topics, and if I cut it, then I'm cutting it really early because then the second topic and then go right into the review. I thought about it long and hard, and well, that was the irrational choice I decided to make. Okay. I got a great idea. I'd like the arc length of this thing. Now, this is kind of tricky. Why will this be tricky? Why will this be tricky?
You can only integrate, or you can only derive one variable.
Well, yeah, is this a function?
Not a bunch.
It's not a function. How do we get past that? How have we done this in the past? We did this problem when we introduced implicit differentiation.
Top half.
Top half, bottom half. Let me ask you a real simple question. What if I only compute the top half? Can I take that value and double it? Do you guys like that idea? That's what we're going to do. That's the oh duh. I can't do a whole circle because it's not a function. There's no dy dx. But if I do top half, bottom half, and go, oh, the top half and the bottom half are going to have exactly the same arc length, so let's just do the top half and double it. Are you good? So what is the top half? That would be y equals the square root of r squared minus x squared, or if you will, probably easier if I write it like this. This is the top half. So here's what I can say with certainty. I'm going to write my answer like this. Now, this point right here is the point r comma 0. This is the point negative r comma 0. What will my x coordinates go from? Negative r to positive r. Now, I have no idea what my integrand is yet, but does everyone agree that it's going to have this form?
Yes.
And I'm doubling it because I'm doing only the top half. So we need to take that y, find the derivative, do 1 plus the derivative squared under the root. There's a lot of stuff going on. Are we making any assumptions? No, we just know that's the equation.
Can you change the negative r on that to 0 since we're doing 2?
Well, okay, not yet. No, the negative r, the x values are going from negative r.
Okay.
That's what that is.
Yeah.
The 2 is because it's top half, bottom half. Now, Chase is already on this. Chase loves symmetry. You ever look at Chase? He's exactly the same on both sides. It's incredible. He sees symmetric limits, which we may be able to take advantage of later, but I won't know until I find the integrand. So that's why I'm not doing anything yet, because I need an integrand that's even, and we haven't found it yet. So what is dy dx? Oops. This shouldn't be too bad. So it'll be what? 1/2 r squared minus x squared to the negative 1/2, and the chain rule factor will be positive or negative?
Negative.
Negative 2x. 2's will cancel, so I'll get negative x over. How about if I just write it like that? We have done a version of this way back when we first learned implicit differentiation. We had to do this type of derivative. Now, next thing I need 1 plus the square of the derivative. So 1 plus the square of this. So that would be what? X squared over r squared minus x squared? Agreed? If I put this over a common denominator, then won't this be r squared minus x squared plus x squared? Ooh. Ooh.
R squared.
I like this. You guys like that so far? That's not bad. That's not bad at all. Okay, that's 1 plus the square of the derivative. Now we need all that under the square root because my integrand is this. So this will be 1 plus, oh, I'm sorry. We got it right there, sorry. Yeah, r squared over r squared. I was about to do the whole thing again. R is the radius. So can I pull the r squared out?
Yes.
Everybody okay with that? That's my integrand. There's no shortcut. You got to do everything we did pretty much on every problem. Get it to this point, 1 plus the square of the derivative. Now I can finally state the problem. Okay, now r is a constant. Is that integrand odd or even or neither? What do you think? Everything's either a constant or a squared.
Even.
That's even, isn't it? Because constants are of even degree. So can I use symmetry?
Yeah.
And what will symmetry allow me to do?
Double it again.
0 to r and double it. That r is a constant, and a lot of us, when we see that r there, it's distracting. We're looking at the r, not knowing what to do with it. Does it figure into the final answer? No, it's just a coefficient. So I'm going to put that r on the outside, just so I don't get confused. Can I do this? Yeah.
So now we're just kind of doing like the arc length of the top right quadrant now.
I'm sorry?
So the interior is kind of like the top right.
Yeah, actually, Chase is correct. If I only look at the integral itself, it's kind of this, isn't it?
Yeah.
Well, except and the r, because it's 4 of them. Now, how are we supposed to do this one? Or is this exactly an antiderivative formula that we have on this test? It is. There's no substitution. This is a formula. Oh, but in the formula, it doesn't say r squared. It says a squared. You guys got it? What is this?
Sine inverse.
Inverse sine. Beautiful. Now, does inverse sine, I know the 1 over r comes in there somewhere. Does inverse sine get the 1 over r?
No.
No. Inverse tan, inverse secant, inverse sine's the only one that doesn't. You okay with that?
Yes.
From 0 to r. Huh. Okay, so this is 4r times what? Times inverse, sorry, I got too much going on here. Inverse sine of 1 over r times r, that would be 1, minus inverse sine of 0. Let's start with the easy one. The inverse sine of 0 is? Sine of what angle is 0? 0. Ooh, like that one. That one's 0. Sine of what angle is 1?
Pi over 2.
Pi over 2. All right, so my answer is 4 times r times pi over 2, which is 2. I'm feeling this strange sense of deja vu. I've seen that formula before.
Circumference.
Isn't that the circumference of a circle?
Mhm.
Oh, but didn't we already know that? Actually, not until just now, because it's not possible. There is no mathematics that exists until what we just did. You've always known that. This is where it came from. Now, if that's not cool, I don't know the definition of cool. That is. Now, I have to warn some of you. When you get in your cars today and you start driving home, some parts of this lecture are going to take a delayed reaction. And all of a sudden you're going to be on the freeway and then, whoa, that oversense. Be in the slow lane, because I don't want to hear about an accident because the coolness caught you while you're on the freeway and you finally realize, oh my God, we just derived one of the single most important geometric formulas that I've known for my whole life, and it can't be derived except for what we just did.
We'll be responsible.
That is so crazy cool. Maybe today's the day to Uber. I don't know. It's just, no accidents. Isn't that great? So I said there's only 3. This is, we've just done 2 of the 3. The third one's really nasty. I don't want to do the third one because I want to move on now. Arclength is a powerful tool that we use in all 3 semesters. So you say, how do you use it in Calc 3? Because I want the curve that's going through the room in 3 dimensions, and I find the length of that curve. Whoa. Now that one feels very complicated, but by the time we get to it, it's actually probably the easiest of the bunch because of everything we've had before it. So the three-dimensional arc length really isn't a problem. It's what we do in Calc 2. The way we do it in Calc 2 is different than Calc 1. We do what's called a parameterization that allows us to introduce new variables, expand what we can do, and then we take that concept and move to Calc 3. So that's literally the only Calc 2 concept we do in Calc 3 is for arc length. Okay? Any question on that? All right. Now, the most complicated derivation maybe of all, maybe in the entire 3 semesters, is the next one. And this is one that I kind of snicker at because the textbooks, every textbook gives the correct formula. I've never seen a derivation done in any textbook whatsoever. I've never even seen an attempt at a derivation. And what's best of, the author, Swakowski, was the most popular textbook on planet Earth for generations. He's been dead for a long time. But we used it at Mesa College for 20 years. In Swakowski, he says, you know this from geometry, and then he gives you the formula. The problem is that I know a lot of highly educated people who have no idea where the formula comes from because it's so obscure. Okay, and that's what we're going to do next. So here's the thing. We're going to start with, like we did last day, I'm going to take a region in the xy plane bound by the x-axis, and then I'm going to rotate it. Just like we did before. Right, so we've got this kind of thing going here, right? So I think that gives it proper perspective. I know how to find the volume. In fact, we have 2 ways to find the volume. If I slice it vertically, they're disks. If I go horizontally, they're shells. I don't want the volume. I want the surface area. Now that's a very different animal altogether, isn't it? If I take this, volume is what it holds. Surface area is the material that I used to make this. So in our classroom, think of it another way. Volume is, if I filled this room with water, you know, how much water will it hold? But the surface area is the materials that I needed to make the walls, the floor, and the ceiling. Everyone understands those are completely different animals because volume is 3-dimensional, surface area is 2-dimensional, first of all. So they're not even the same units. So how in the world would I find the surface area of this? Well, we're going to slice it up and do a bunch of things. But before we get there, we need to go through some geometry, and some of it's very obscure geometry. We're going to come back to that, but it's going to take us a little while. Okay, so I'm going to go over a couple of facts that you've been exposed to, but you might not remember today. But these are things that we reintroduce many times. Between Calc 1, 2, and 3, the next thing I'm going to do, I probably do 10 different times over the 3 semesters, so you get more familiar with it. Okay, I have a circle of radius r. This is the center of the circle. So that means this is called a central angle. If I just simply picked a random spot, then none of this would make any sense. But I'm going from the center of the circle, so that's the radius of the circle. This is the length of the arc, and this will be the area of that portion. Now, what is that pie-shaped wedge called? It actually has a name. We may have mentioned it in this class. I'm not sure if we have or not. Does anybody know what that's called? We did this at the very beginning, I think, when we were doing the squeeze theorem. Starts with an S. Sector, good. It's called the sector of a circle. When I take a sector of a circle, right, that's, you know, yeah, you got the Thanksgiving pie, and you guys cut it perfectly in the middle, then all the little pieces, those are called sectors. The pieces of pie, literally are called sectors. There are 3 equal ratios that we use here, and we use all of them on a regular basis. Theta is, think of this as the fraction of the circle that I used. So the angle here is to the angle all the way around, as the area here is to the area of the whole thing, which would be pi r squared, which is to the arc length to the whole way around. So keep it really simple. Let's suppose my sector represented exactly 1/4 of the circle. Then shouldn't this be 1/4 of the angle, 1/4 of the area, and 1/4 of the arc length of the whole circle? So that's why those 3 ratios are equal. The most common 2 we put together are these 2. But we're going to actually put together the last 2 today, okay? I would like to be able to describe the area of the circle in terms of the other stuff. So can I say that the area equals S over 2 pi r times pi r squared?
Yes.
Now what does this give me?
A half SR.
Okay? Did I get everything correctly? I think I got everything correctly. Okay, so
No, you didn't.
make sure I got everything correctly.
Yes.
Yeah, so that is 1/2
SR.
SR, if I go that direction. By the way, it turns out there's 3, I'm gonna show you the other ones, because you use all of these. If I wanted to find the area with the first 2, we'd say area is theta over 2 pi times pi r squared, which is 1/2 r squared theta. That's actually considered a very important formula. And if I put the first and last together, I get S equals theta over 2 pi times 2 pi r, which is simply, what, r theta. That's a crazy one, that the length of the curve is just r times the angle in radians. Everything has to be in radians. So this is the part that I wanted to look at here. The area of that sector is 1/2 the arc length times the radius. Okay, well that's kind of an interesting thing. Not really sure what to do with that. Now, we'll figure this out in a moment. Consider the following. This is a circular cone. Do we know the volume of the cone? Yeah, we actually do. Now we talked about a pyramid versus a prism, it's 1/3. The cone versus the circular cylinder, it's 1/3. We know the volume of the cone is 1/3 pi r squared h. That's a piece of cake. Do we know the surface area of the cone? No. Turns out this is one of the more obscure formulas in geometry. If you had, how many had a formal high school geometry course? Not it was bits and pieces of geometry mixed in with a whole bunch of courses, but you actually had geometry. Did you spend any time on shapes and volumes and surface areas and things? Hopefully you spent a little bit. Surface area of a cone is kind of obscure. It is kind of obscure. If this is the radius of the cone and this vertical is the height of the cone, we call this the slant or the slant height. I don't want to use an S because I already have an S over there, so I'll just use the word slant. Okay? I would like to find the surface area of this cone. How the heck am I supposed to do that? It could be bigger, but... Okay, can everybody see my cone? I have a cone. Okay, I'm not going to put it on my head, but I have a cone. I want the surface area of this cone. Now, do I know certain dimensions? Yeah, let's say I know all 3 of those things. I want the surface area of this cone. How would I do that? Well, if I take a set of scissors and I slice my cone, what is the shape that it turns out to be? Again, you won't find this on YouTube or in any math book ever written as far as I can find. I spent my whole life looking for this and no one does this except me, which is unfortunate because you can't get any of the formulas without knowing the geometry, and I don't want you to memorize. See this? This is the sector of a circle. Do I know the area of this piece in terms of the circle? It's right here. All I need is the arc length and the radius. Now remember I said in the cone, assume you know this, and you know this. You know this. If I gave you a cone, could you measure each of these rather easily? Yeah. Heck, if I took out an ice cream cone and I set it on the counter, I just take out a ruler and tell you the height. I put the ruler on the angle and I tell you the slant, and I put it in the middle. Those are trivial. Those are absolutely easy. I can measure those or give you those. I'm starting with I gave you this, I opened it up, and now I'm here. So in terms of the cone, what is this in terms of the cone? Isn't that the circumference of the cone? Does everyone see that? That this is the circumference. Sorry, it's hard to read. In terms of the cone, what's the R? Okay? So bear with me. I'm going to erase this stuff here. This produces a very interesting formula. That means the surface area of this, assuming I know all of these things, is 1/2 the circumference, which in this case would be, of the cone would be 2 pi r, times the slant. Now, if all I'm talking about is a cone, there's no curve, there's nothing else, I just have a cone. Most geometry books would just go ahead and use an S for slant because I have the cone. I don't have any other shape. There's nothing to confuse S with. So in this case, I'll just call it an S for a moment. Now, this sounds very corny, I know, but one of the most obscure, if not the most obscure formula that most high school geometry students would ever do is something like the surface area of a cone. That's a very obscure one. It's, to remember it can be very taxing. Now, I have a really terrible analogy. I taught high school for several years, many years ago, and I taught at a private rich kid school where every kid, no joke, drove cars that were worth significantly more than any teacher made in a year. We had kids with chauffeured limos arriving to school. One kid it was the black tinted windows and the 4 big dudes in the suits carrying, well, artillery. Yeah, it was crazy. But we would do this formula, and these are kids who, they didn't know math very well, but they knew money really well. And so the way they would remember this formula it was very taxing. It was a very taxing formula. Say the formula out loud. Surface area is pi rs. I never had a kid in all the years I taught have difficulty remembering this formula because it was very taxing. If you don't get it, what does it rhyme with? IRS, yeah. That's how every kid remembered the formula, rhymed with IRS. It was very taxing. I know, whatever it takes to remember a simple formula. But that is exactly the surface area of the cone. Life is good. That's exactly what it is. You guys go, yeah, I knew that formula. I knew it's pi times the radius times the slant height of the cone. Now, just for fun, here's what we're going to do. We're going to slice the cone, and I'm going to slice off the top of the cone. I'm going to slice off the top of the cone, leaving this. As obscure as that formula was, this is 10 times more obscure. I'm now looking at this shape. Now, you know what this is? Have you ever been to the circus? Right, what do the elephants put their foot on? This guy. Everybody know what I'm talking about? The elephants at the circus, they put their foot on this guy. This is called the frustum of a cone. That's the one I need the surface area for. As bad as that one was, we actually need this one. You know why? Because when we slice this up, that's the shape of our slices. They're not going to be discs. They're going to be those. Oh my gosh. So, like I said, there's some obscure geometry involved, but it's crazy cool stuff. Like I said, later on today, it's going to hit you and you're going to be going, whoa. Okay, so let me do something really simple from a geometry standpoint. I'm going to just have a random triangle here. Tell me about similar triangles. Remember the term similar.
Means that they might have the same size.
It means that they're not necessarily the same size, but the same
Angles.
shape. So in triangles, they would have exactly the same angles. One of the simplest ways to create similar triangles is to simply draw a side that's parallel. And some of you remembered some of these theorems. Now, my little triangle and my big triangle both share this angle, don't they? Here's 2 parallel lines cut by a transversal. These were called, remember? Corresponding angles. It's a simple proof to show those 2 angles are congruent. Here's 2 parallel lines cut by a transversal. These 2 angles are congruent. And you just said it correctly. If I have 2 triangles and the angles of one triangle are congruent to the angles of the other, the triangles themselves are similar. They're not necessarily the same size, but they're exactly the same shape. So the little triangle and the big triangle are similar triangles. Well, why is that important? Because similar triangles, the corresponding sides have equal ratios. So for example, if this side were 2/3 the length of this side, then this side would be 2/3 the length of this side, and this side would be 2/3 of the length of this side. All the ratios correspond. That's the geometry I need to do the next thing. Okay? So if this were true, so let's go back to this picture. When I cut off the top, when I'm staring at this with one eye closed, I don't see a cone anymore. What do I see? When you stare at this, I'm going to have all you do this. Stare at this and close one eye. What do you see?
A triangle.
You see a triangle. In other words, can I apply this to this? Yes, exactly. I see a triangle, which means that the frustum of the cone is acting like this portion. Oh, so to make it easier on ourselves, so let me draw something that actually is a little more uniform. Okay. So I had a circular cone, and I'm going to cut off this. All right. So don't forget this part here. So this would be the radius of the big cone. This would be the radius of the little cone. Do you agree?
Yeah.
So let's just call this, how about R1 and R2? Now, obviously, this side would be two R1s and this side would be two R2s. That's not really the question. Now, let's call from here to here, let's call that slant 1. Then let's call from here to here, I don't know, how about slant 2? It's pretty profound, huh? So far, so good? Can you tell me a true statement? Think ratios for a moment. Let's start with R1 is to, or you say R, I don't care which way I go. R1 is to R2 as, does everyone agree with that statement? Great. That's a good starting point. The thing is, I need this portion right here. I have the R1 and the R2, but let's call that piece, for lack of a better name, let me just call this piece from here to here just S. Now tell me, what does S equal?
S1 minus S2.
Good. That's huge. I have everything I need to now do this. Here's what I would like to do. I would like to describe the things here, but only using S. Not S1 or S2, but only using R1, R2, and S. And that's going to be a little bit tricky. Let's go back to the top for a moment. If this is true and I multiply both sides by R2 times S2, wouldn't it be true then that R1 S2 equals R2 S1? Do you agree with that? Not really, right? Not really going out on a limb. I multiply both sides by the common denominator and got that. Now, if S equals this, then wouldn't that make, how about S1 equals S plus S2? Would that be true?
Yeah.
Then let's substitute, let's get rid of the S1 because I don't really need the big arc. I need S. True? All right, let's go ahead and distribute that. Okay. Now, how about we throw this guy that way? Then what do we have on the left side? Then on the left side we'd have R1S2 minus R2S2, and on the right side we'd have R2S.
Are we gonna factor out the S2?
That would be a good idea. So now what do I have on the left side?
S2. Yeah, let's do it.
Okay.
Divided by R2.
Yeah, Yeah, not yet though. I can, but I really don't want a quotient. What I want to get is, I want to get the relationship, okay? If I'm trying to find, we know that the surface area of the big thing is this, agreed?
Yes.
Does everybody agree with that? Now, I'm going to stop there for a moment. The surface area of the big guy is this. I want the surface area of this. So technically, isn't the surface area I want the big surface area minus the surface area of the top cone?
Yeah.
Does everybody agree with that? So what is the surface area that I'm actually looking for would be what? Pi rs, in the case of the big cone, it would be pi r s1, because that was the big one, minus what? Minus pi r s2.
Do we also have to indicate which bar we're using for that?
Oh, thank you, sorry, you're right. Thank you, Cece, I can't see from over here. So what was the first one? It would be R1 now, thank you. Cece, you're absolutely correct. Yeah, it does matter. Do you all agree that this is what I'm looking for? I can't use an S1 or an S2, I need it to be 1. Now, with this statement, now we go back up to here. Do I have any of these terms sitting here? Yeah, I got them in a few different places. In fact, let me go back to that guy. Actually, I'm going to go backwards a little bit, because I think we have everything we need right in front of us. Let me go back to this statement here. If I throw this guy over, then I have R1S2 minus R2S equals R2S2. I have an R2S2 right here, don't I? I just need to be able to substitute something with an S in it at this point. So this would become pi R1S1 minus pi times what? R1S2 minus R2S. Okay? So if I distribute, I'll pull out the pi's. That'll be easier. R1S1 minus R1S2 plus R2S. What's S1 minus S2? That's S. So what do I have now? Pi times R1S plus R2S, or R1 plus R2S. We did it. We're not finished. We just figured out a way to find the surface area of the frustum of the cone only dealing with this length, not the original length. And that's the key, we need that length. So I'm going to do something completely crazy, not that I have so far today. Go one more time. The surface area of the frustum is, how about if I wrote it this way, just for fun, 2 pi times a half R1 plus R2 times S. What a crazy notion. Why would I do it like that? It's, by the way, is that the same thing? You see I have 2 times a half there. Is that the same thing exactly? You just took 2 exams. Exam 1 and exam 2, and you took half their sum. There's another name for that.
Average?
It's called the average. We're going to be taking a limit at some point. The average R is just going to become R. It's going to be 2 pi times the R times the S. Whoa. Let's take an arbitrary slice here. I'm not squaring these off. That was for volume. I'm doing surface area. I will not get the same answer if I square these off. No, what I'm doing is I'm angling this off. And what is the shape that I just got? I got the frustum of a cone right here. You with me? I got the frustum of a cone. If I can figure out the surface area of this slice, then I can tell you exactly what we need to add up in order to get our integral. Well, I know what it is. We just figured it out. It's going to be 2 pi times the average radius, which in this case, won't the average radius just be the y value? The height? But what will the slant be? The slant will be the same s. It'll be the arc length. That slant distance is exactly the arc length, isn't it? So we now have a formula that we can add up. The area of the ith slice, if you will, not using that denotation. The area of the ith slice is 2 pi, and I said the y value, so times the average height, and then then this guy here would be 1 plus, and then yikes, that looks scary. What are we going to put in here? Well, obviously we're going to put f of x. So whether you write it as dy dx or f prime of x is not really that critical. So when I do the Riemann sum and I go directly to the integral, we can now say the surface area is, just like before, from beginning to end, we'll call it a to b. It's 2 pi f of x 1 plus dy dx squared dx. Now that is crazy complicated, but that's the formula. And what makes me laugh is the calculus books will say, you know this from geometry. Because you all learned this in geometry, right? Probably not. That is a crazy formula. That's surface area. Does that look a lot like arc length? Yeah, it's got the arc length parameter as part of it. And strangely enough, because of this extra piece, there are a lot more problems that we can integrate. The problem with this is, okay, if I think of a number, think of a simple integer squared. Okay, now add 1 to it. Is it a perfect square anymore? If you take a number and square it and then you add 1 to it, it's not a perfect square anymore, is it?
No.
Unless you start with 0, it's not a perfect square. So that means the 1 plus the square of the derivative is never going to just come out of the square root. It's just not going to. So I'd have to use a u substitution or be a little bit clever. And in the arc length, we didn't have a chain rule factor sitting around. But is it possible we now have a chain rule factor sitting around?
Yeah.
Oh, so let's do one. We'll do a simple one. As if there was a simple one. Okay. Let's consider the region bounded by y equals, let's say, x cubed, y equals 0, x equal 2 is rotated about the x-axis. Find the surface area of the resulting solid before we asked for the volume. Now these shapes will not have holes in them. These ones won't. These will be one big solid object. It's too hard to work with things with holes. We could do volumes that way, but we don't really want to do surface area that way. So if I'm going to draw the picture of this,
Is that y equals x squared?
it's x cubed. So, kind of ugly, I know. So we've done this one before, or a version of it. This is kind of a bugle. I don't want the volume. I want the surface area. Yikes. Well, since it involves this, then I still need to do this part first. Okay? So let's start with that part. All right. dy dx is what? Okay, 1 plus dy dx quantity squared then is
1 plus 9x to the fourth.
okay, so that's what's going inside the square root. Can I go ahead and write the integral down directly?
Yeah.
Yeah, because this is the formula. I don't need to do the pieces. I needed to do this piece. So I can now say with certainty, area is 2 pi f of x is y cubed times the square root of 1 plus 9x to the fourth dx. X is ranging from what to what?
0 to 2.
0 to 2. This looks big and scary. 2 pi is just a constant. That really doesn't bother us. Can I do this as a u sub?
Yeah.
Do I have everything just right in terms of degrees?
Mm-hmm.
Yeah, I do. Can't do this for all problems. We can certainly do it for this problem. What should I make my substitution?
1
Let
plus
u
9 to
be
the fourth.
1 plus 9x to the fourth, then du is
36x to the third.
okay. As x goes from 0 to 2, u will go from 1 to, might need a calculator, 1 plus 9 times 2 to the fourth power.
145.
Yes. Now, I almost have everything perfect except I don't have exactly the right coefficient yet. So I'm going to do two things. First is I'm going to take the 2 pi and put it on the outside. It's in the way. Now, what do I need there?
36.
I need a 36x cubed. So will that work, what I just did there? I always do it this way. I don't like rewriting over and over. I just write over the top to some degree as long as I can tell what's going on. So now, this is pi over 18 u to the 1/2 du, and my limits are 1, 245. Now, the answer is going to be ugly, but getting to the answer should actually be fairly simple because that's a pretty easy antiderivative at this point. Okay? So what do we got? U to the
3 over 2.
times 2/3. I think we did this one already, so that's pi over 27. Okay, I'll do this one. 1 to the 3/2 is 1. Okay. $145 doesn't have any factors that are perfect squares. 144 does. In other words, 145 is one more than a perfect square. And that's about the best we can do. It's ugly, but it is correct. All right, we're going to do one more. And this is, again, I know I'm killing you with cool today, but this is maybe the coolest one. I don't know, 2 pi over 2. Let's make a sphere. Now, we did this the other day when we did a volume. Remember what we did? We took a semicircle, we rotated it about the axis. We're going to do the exact same thing. We're going to make a sphere that way, but then we're going to find the surface area. So, we're going to rotate y equals r squared minus x squared about the x-axis. Okay? That will make a sphere, not a circle. We'll make a sphere. Okay? I want to slice this thing. So if I'm doing this, right, I now have a three-dimensional thing. When I do my slices, is it this or is it this? It's this, because that's what I rotated. Okay, so I'm not, when we did volume, I pulled this out as a disk, correct? So I needed the whole thing. That's not what this is. This is, I went from here to here, because that's, in my picture, that was the y value, okay? Now, second thing I need to do is, I need to do the 1 plus the square of dy dx. And I think we did that, I think we did this already. Did we do this problem already today? Did we do 1 plus the square of this for arc length?
Yeah.
Just go back in your notes a half hour, just to save ourselves some time.
Yeah.
What was that? It was exactly, I believe, r squared over r squared minus x squared. Isn't that what we did? So we've done this in the last hour. We did this problem. We did 1 plus the square of the derivative, and we got this. And I need the square root of that as part of my integrand, but that's not the whole integrand. So I can now say the arc length is, now that point there is r comma 0. We should be getting familiar with this. So r is going, or excuse me, x is going from negative r to r. I have 2 pi this times the arc length parameter, which is the square root of this.
Which was just
Hey, wait a minute.
R.
Did those cancel? Isn't the root of a quotient the quotient of the roots? Can I make this, can I just do that instead?
Right?
So that I can,
Yes.
oh my gosh. So what do I got?
IR.
So what is this? Oops. And that is,
Question. Didn't we have, should we have changed it to a symmetric? Like one time?
didn't need to, because we're already done. Yes, we could have done symmetry. What did we just do? We just took a half a circle, rotated about the x-axis, found the surface area, and we found the surface area was 4 pi r squared. Wait a minute, isn't that the surface area of a sphere that we knew as little kids? And once again, can't be derived except what we just did. Like I said before, most of the geometry formulas, anything involving circles or spheres, it requires calculus. But we figured out all these things, haven't we? Volume of a sphere, surface area of a sphere, circumference of a circle, all of that using this calculus. So we just figured out, by the way, are we using any circle properties in these calculations? No, we're just straight out calculating. So if we had never even heard the word geometry, we don't even know what a circle is, we've lived under a rock in a cave, I don't know, we would have still come up with this answer. Cool. So now you go back in time, right? And maybe go before the ancient Greeks, and then you'd be the smartest person in the world because you know all these formulas, and you can derive them and prove them. Okay, go ahead and stop that. All right, so the last